Magnets Push, Magnets Pull by David A. Adler, illustrated by Anna Raff, copyright Scholastic Incorporated. Magnets push, magnets pull. A world without magnets would be a world without computers, printers, cell phones, televisions, vacuum cleaners, and microwave ovens. It's a magnet's invisible pulling and pushing force, called magnetism, that helps power all these devices. Magnets are attracted to anything made of iron, steel, nickel, or cobalt, and some less plentiful metals, including neodymium and samarium. There are two kinds of magnets, simple magnets and electromagnets. You are probably most familiar with simple magnets, the kind you find in toys or use to hold papers to your refrigerator doors. Do you have a simple magnet? If you do, you can use it as a metal tester, but be careful with your magnets. Do not bring it close to a watch, clock, computer, television, or any delicate instrument. It could damage them. Test some US coins. Does your magnet stick to any of them? It shouldn't. US coins aren't made mostly of iron, steel, nickel, or cobalt. Pennies, nickels, dimes, and quarters are mostly copper. Place your magnet on the hood of a car. Does it stick? It should. Most cars are made from steel. Take a few cans from your pantry. Does your magnet stick to them? It may stick to some and not to others. Some cans are made from steel. Others are made of aluminum. Simple magnets come in many shapes and sizes. If you have a magnet of any size, you can use it to test the force of magnetism. Place a few steel paper clips on a table or any flat surface. Put the magnet on the same surface about 1 foot away. Slowly move the magnet toward the paper clips. You're just moving the magnet, but the paper clips will soon be moving too. They'll slide across the table and stick to the magnet. Your magnet's invisible pulling force pulled the paper clips across the table. If your magnet is strong enough, it will work through paper, water, and glass. Place a paper clip on a sheet of paper. Hold the magnet beneath the paper. Without ever touching the paper clip, you should be able to use your magnet to move it. Drop a few paper clips in a shallow bowl of water. Hold your magnet at the surface of the water. If the magnet is strong enough, it will pull the clips through the water. With a really strong magnet, you would be able to hold it against the side of the bowl and move the clips on the other side of the glass. A bar magnet and some iron fillings, available at most hardware stores, will help you understand magnetism. Cover your bar magnet with a white, unlined sheet of paper. Center the paper over the magnet. Sprinkle the iron fillings onto the paper. Gently tap the paper. Now look at the iron fillings. They should form a pattern showing the magnet's magnetic field. The pattern shows where the magnetic force is strongest. It's strongest by its two ends, where many of the fillings should have gathered. The two ends of a magnet are called its poles. Each magnet has two poles, a north pole and a south pole. You can test your bar magnet to see which is its north pole and which is its south pole. Tie a thin string around the middle of the magnet going lengthwise. Tape the other end of the string to the bottom of a wooden bookshelf or table. The string should just be long enough to let the magnet hang freely. Be sure there are no other magnets nearby. Nothing made of iron, steel, nickel, or cobalt. Nothing to confuse the magnet. Gently tap the magnet. When it stops moving, one pole should be pointing north and the other pole pointing south. Ask an adult which direction is north. With a marker, write N on that end of the magnet. Write S on the other end. Sailors, hikers, pilots, and others use compasses to help them find their way. The needle inside a compass is really a magnet. One end of the needle always points north. Look at any globe. The most northern part of the globe is labeled North Pole. The most southern part is labeled South Pole. The poles of every magnet always point north and south because the Earth is a huge magnet with a relatively weak magnetic field. Its magnetic pole is strongest at its two ends, its North Pole and South Poles. Watch two bar magnets. You can see how north and south poles attract and repel each other. The poles of bar magnets are often marked N and S. If yours are not, you can test them by letting them hang freely, tapping them both, and then seeing which way each pole points. Then mark both ends of each magnet with an N and an S. Place both magnets on a table or any flat surface. Place them at least a foot apart. Line them up with one pole of each magnet facing the other. Slowly move each magnet towards the other. If you have an N pole moving toward an S pole, you'll feel a strong magnetic attraction between the magnets. The pole of one will stick to the pole of the other. Opposite poles attract each other. The only natural magnet is lodestone, a stone loaded with magnetite, a magnetic mineral. All other magnets are man-made. You can make a magnet. Take a large steel paperclip and hold it close to some iron fillings. If the fillings don't stick to the clip, you know the clip is not magnetic. Now take your bar magnet. Start with one pole of the magnet pressed against one end of the paperclip. Rub it along the clip to the other end. Do this again and again, 25 to 30 times. Rub the same pole of the magnet against the clip, always in the same direction. Hold the paperclip close to some iron fillings. Does the clip attract the fillings? If it does, the paperclip is now a magnet. Why were you able to turn your paperclip into a magnet? All metals are made of molecules, minuscule particles too small to see. Scientists tell us that the molecules that make up iron, steel, nickel, and cobalt are tiny magnets that are normally a jumble. When you rubbed the paperclip, you aligned the tiny magnets until all the northern poles were pointing north and all the southern poles were pointing south. With all the magnets lined up, the paperclip became one large magnet. Before, after. Magnets can lose their magnetic power when they are hit really hard or exposed to extreme heat. Magnets can also multiply. When you break a magnet in half, you create two smaller magnets, each with a north and south pole. Electromagnets, sometimes called on and off magnets, use electricity to create their magnetic fields. When an electric current passes through a wire, it creates only a weak magnetic field. Wrapping a wire with an electric current flowing through it around an iron rod turns the rod into a magnet. The tighter the coils of the wire, the more turns, and the stronger the electric current, the stronger the magnet. If the electric current is turned off, the electromagnet loses its power. That's why they're sometimes called on and off magnets. Electromagnets are used in buzzers and bells, computers, televisions, and many other electric devices. They power all electric motors. You can't see magnetism, but you can see what it does. It's difficult to imagine a world without magnets. Glossary. Attract, to pull toward. Electromagnet, a device that uses the flow of electricity to create a magnetic field. Force, the power to push or pull something. Magnetic field, the area around a magnet that attracts certain metals. Magnetism, the unseen power to pull and push certain metals. Pole, the point on a magnet where its magnetic force is strongest. Repel, to push away. Simple magnet, magnets that do not need an electric current to attract certain metals.